companies use the following guidelines to calculate reserves. In making calculations, they classify oil reserves in two broad categories. The first is known as proven or proved reserves. Proven reserves, like the name implies, is calculated with the most certainty. Indicators from actual production or formation tests are used. The numbers also include the assumption that operational facilities to process and transport the oil reserves to market are in place and that the reputation of the company making the claim is believable. The second is known as unproven or unproved reserves. Unproven reserves are even less certain. In unproven reserves, standard engineering procedures and tests have not been performed, so the size of the reservoir and its dimensions are not fully known. Also, because producing these reserves may depend on better economic conditions or improved technological developments, estimates of these unproven reserves are imprecise. Nevertheless, we still must derive estimates, and there are several methods available depending on the development stage of the reservoir. First, let's look at what is called the volumetric method. It is used in the early days of a field's development when only rough estimates of the dimensions of the reservoir are known. Let me illustrate how reservoirs are calculated using the volumetric method. Our objective here is to figure out the original oil in place, OOIP. We do that by obtaining pertinent data that we plug into the following formula. OOIP equals the unit of measurement constant, K, times the area of the reservoir, A, times the thickness of the reservoir, H, times the porosity of the reservoir, phi, times the oil saturation, SO, where SO equals 1 minus SW, and where K equals 7,758 barrels per acre foot. Thus, OOIP equals 7,758 barrels per acre foot times A in acres times H in feet times phi times SO. Therefore, if a typical reservoir has the following values, phi equals 20%, SO equals 70%, A equals 5 kilometers squared, H equals 20 feet, then we will be able to find OOIP. First, we convert kilometers squared to acres for the area. Since we know that there are 247 acres in 1 kilometer squared, we write 5 kilometers squared times 247 acres divided by 1 kilometer squared equals 12,350 acres. So now we are ready to find OOIP. OOIP equals 7,758 times 12,350 acres times 20 feet times 0.20 times 0.70 equals 27 mm barrels. Note, M equals 1,000, mm equals 1,000,000. Now we know that we have approximately 27 million barrels in the reservoir. Next, we need to calculate the amount of oil we can recover. To calculate that, we use this formula. Recoverable oil equals OOIP times the recovery factor, RF, divided by the shrinkage factor, beta, or recoverable oil in stock tank barrels equals OOIP times RF divided by beta. For example, if the recovery factor equals 0.35 and beta equals 1.2 barrels per stock tank barrel, then recoverable oil in stock tank barrels equals 27 million barrels times 0.35 divided by 1.2 barrels per stock tank barrel equals 11 million stock tank barrels. In this calculation, we use typical RF and beta numbers, but in the field, we would be using the actual numbers from the calculations made from the reservoir's fluid characteristics and flow rates. Therefore, approximately 11 million stock tank barrels can be recovered from this field. This number, of course, reflects the recoverable rates at existing technology. Over time, with enhanced technology, recovery rates could go higher. The third thing we calculate is the amount of gas that comes up with the oil that can be produced. This ratio is calculated when the well is first being tested, and its volume can be calculated using the following formula. Associated gas reserve equals OOIP times GOR, where GOR is the gas to oil ratio as measured before production actually starts. When measuring gas, we use standard cubic feet, SCF. This unit defines the volume of gas to be at standard atmospheric conditions of 60 degrees Fahrenheit and 14.7 psi. Also keep in mind that gas volume in the reservoir varies tremendously from gas volume at the surface. Note also that the GOR will continue to change as oil is produced. Basically, this is the volumetric method. It is primarily used as the first method to calculate reserves. Additional methods include material balance method. It is used after about 10% of the reserves have been produced after more accurate data has become available. Since reserves have observable reservoir pressure declines and changing production values as oil is extracted, this data can be used in the materials balance method, giving greater accuracy in calculating proven reserves than the volumetric method. Another method to calculate reserves is called the reservoir modeling or simulation method. By the time this method is used, a great deal of high-quality data from the reservoir has been acquired. Now, detailed computer models of the reservoir can be constructed to simulate or show the depletion process. Because these models are constructed after good, accurate data has been obtained, these simulations can be quite accurate. When using the depletion decline curve method, the reservoir is nearing an advanced stage of depletion. Since its production rate has been steadily declining at a predictable, constant percentage, this method in predicting remaining reserves is preferred. Plotting the production rate against time, the decline can be illustrated graphically as a relatively straight line and is used to determine the economic limit of the reservoir. As you can see, the volumetric method is used very early in the life of a reservoir. After production starts, the material balance method comes into play. Mature reservoirs rely on reservoir modeling and simulation methods. Finally, the depletion decline curve is utilized to determine the field's economic limit. Of course, all of these measurements and calculations are dependent on the accuracy of the data from the reservoir, and at best, these measurements and calculations can only be described as estimates. As more data is made available about the reservoir, as economic conditions improve or worsen, and as better enhanced recovery procedures become available, oil companies revise their estimates to better reflect this new information. As these estimates are released into the public domain, they are only as good as the reputations of the companies making the claims. Because of international legal consequences, international oil companies usually apply best practices when quoting their reserves. National oil companies' estimates, on the other hand, depend on various political considerations and may be more suspect. Because reserves, either proven or unproven, are only rough estimates, it is important to remember that they are not counted as assets on the balance sheets of oil companies. However, oil industry players keep a sharp eye on these reserve estimates because they are very useful in predicting the future health of an oil company. In this chapter, we examined terms and definitions essential in comprehending the analysis and evaluation of the characteristics and classifications of a petroleum reservoir. Understanding these new concepts then allowed us to describe how hydrocarbons are brought to the surface through primary, secondary, and tertiary recovery drives. Finally, we discussed proven and unproven reserves and how calculating these reserves allow the industry to develop plans for future development and expansion.